Hello, everyone. So last time we looked at induction as a method of proof in mathematics. So last time, induction or mathematical induction. So we saw that it contains a basis step that you verify the statement for n equals 1. And then it also has inductive step. In inductive step, you suppose that the statement holds for n equals k and prove that it holds for n equals k plus 1. Okay, and we saw that there could be so many examples of theorems that can be proved using induction method. Different fields, some of them maybe you haven't taken the relative course yet, but we covered some topics last time and some examples of each type. For example, set theory or number theory or proving inequalities. But I would like to, I did, I think, one example of each type, but because this method is very important in mathematics and I want you to get more comfortable with it, I would like to do a few more examples of those types that we mentioned last time. So let's say more examples of induction method. So example, suppose that n is an odd positive integer. Suppose that n is a positive integer, is a positive odd integer. Show that n squared minus 1 is divisible by 8. It's divisible by 8. So let's see how we can prove this. So solution. Well, our only assumption about n is that n is a positive odd integer. And how can I write a positive odd integer in mathematics? So by assumption, we can write n equals 2k plus 1 for some non-negative integer k. So n squared minus 1 would be 2k plus 1, the whole squared minus 1. So that's going to be 4k squared plus 4k, right? Because then I will have like a plus b the whole squared, a squared plus b squared plus 2ab. So I will have a plus 1 term, which cancels with minus 1 term. And I'm going to be left with 4k squared plus 4k. And then this one, I can write it as 4k times k plus 1. So n squared minus 1, we wrote it as 4k times k plus 1. So we can already see that n squared minus 1 is divisible by 4 because it's 4 times a number. Now, if I can show that the remaining factor, which is k times k plus 1, is a multiple of 2, or in other words, an even number, then we can say that n squared minus 1 is a multiple of 8. So then, our next, we show that k times k plus 1 is an even number for every k bigger than or equal to 0 using induction. So you can show that this is an even number using induction or using division algorithm. But because we are in the topic of induction right now, I would like to do it with induction. So how can I show that this is an even number using induction? So for k equals 0, because I want to show that this is true for every k bigger than or equal to 0. So k equals 0, 0 times 0 plus 1, so that's 0, which is even. So suppose then I can do it for inductive step. Suppose that k times k plus 1 is an even number for k equals L, and you will show that it is an even number for k equals L plus 1. So L plus 1 times L plus 2, how much is this? Because I'm writing k times k plus 1. So I assume that this even number for k equals L, which means, L times L plus 1 is even. And I want to show that this expression for k equals L plus 1 is also even, meaning that L plus 1 times L plus 2 is even. Now, what is L plus 1 times L plus 2? So if I expand this, it's going to be L squared plus 3L plus 2, which I can write it as L squared plus L plus 2L plus 2, right? 3L plus 2, I can write it as L plus 2L, then plus 2. Now, L squared plus L is even by the assumption in inductive step, or induction hypothesis, in other words. This is an even number. And this one is 2 times L plus 1, which is also even. And then even plus even will be even. Because even plus even is even. So this number is even. So we showed k times k plus 1 is even for every k bigger than or equal to 0. So therefore, I can write k times k plus 1 equals, let's say, 2s for some integer s. So I can write it, the number, what was it, n squared minus 1? It was 4k times k plus 1, but k times k plus 1, we said that, we established that it can be written as 2s. So n squared minus 1 equals 4 times 2s equals 8s for some integer s. And that means 8 divides n squared minus 1 as desired. So remember, our final goal was to show that n squared minus 1 is divisible by 8. So we wrote n squared minus 1 as a multiple of 8, which is what we needed to do. So this example, by the way, is one of the book exercises. I think it's question 35 in 5.1. Yeah, 5. All right. Now let's look at another example. This one is question 76, part B. Show that 1 times 2 times 3 times 4 times times 2n minus 1 over 2n is less than 1 over root 3n plus 1 for n bigger than equal to 2. So let's see how we can prove this using induction. So basis step. We have to verify for n equals 2 because the question says that ask us to prove that this inequality holds for n bigger than equal to 2. So the very first n value that we have to use is n equals 2. Then we get the left-hand side. How much is that going to be if n equals 2? 2 times, so it's going to be 1 times 2 times 3 over 4. And I have to show that this is less than 1 over root 7. If n is 2, left-hand side will be 1 over 2 times 3 over 4. Right-hand side will be 1 over 7. So is that right? So this one is 3 over 8, which we have to show is less than 1 over root 7. How would you show that 3 over 8 is less than 1 over root 7? Any suggestion? So this one, we can write it as, so note that 3 over 8 is less than 1 over root 7 if and only if, what happens if and only if root 7 times 3 is less than 8, right? And this inequality will hold if and only if 7 times 9 is less than 8 to power 2, which means 63 must be less than 64, which is correct. So in mathematics, when you want to verify an inequality of this form without using calculator, this is the way to do it. So you can write the inequality that you want to show and then write equivalent versions of it. So this one is equivalent with this one. Because this direction to this direction, I can multiply both sides with root 7 times 8. This direction to this direction, divide by that number. So these two are equivalent. And then this one is equivalent with this one because, well, a is less than b is equivalent with a squared less than b squared as long as a and b are both positive. And yeah, this is, of course, equivalent with this, and this one is true. So that means this one is true, the one that we wanted to show is true. So that means basis step holds. Now let's do inductive step. Suppose that the inequality holds for n equals k, meaning that 1 over 2 times 3 over 4 times 2k minus 1 over 2k is less than 1 over root 3k plus 1. Is the inequality we want to show? Let's assume that it's true. It holds for n equals k, and I have to show that it holds for n equals k plus 1. So we need to show. So the inequality holds for n equals k plus 1 means what? Means 1 over 2 times 3 over 4 times 2k minus 1 over 2k times 2k plus 1 over 2 times k plus 1 is less than 1 over root 3 times k plus 1 plus 1. Right-hand side and left-hand side, if n equals k plus 1, the last term is going to be 2k plus 1 over 2 times k plus 1. Right-hand side, if n is k plus 1, is going to be 3 times k plus 1, which is root. And then, so let's simplify this a little. Now, let me first call this one star. So let's write now star is equivalent with saying that 1 over 2 times 3 over 4 times 2k minus 1 over 2k times 2k plus 1 over 2k plus 2 less than 1 over root 3k plus 4. 3 times k plus 1 is 3k plus 4. Now let's consider, let me call this one, for example, left-hand side. Next, by induction hypothesis, what can we say? We can say that the left-hand side is less than, see the first k terms, 1 over 2 times 3 over 4 all the way to 2k minus 1 over 2k. This guy is less than 1 over root 3k plus 1. So this guy is less than 1 over root 3k plus 1 times 2k plus 1 over 2k plus 2. And so left-hand side is less than this number. So if I can show that this number here is less than right-hand side, then we are done. Because if left-hand side is less than this number and this number is less than this number, then we can say, of course, left-hand side is less than right-hand side, which is exactly what we need to show. So it's enough to show that 1 over root 3k plus 1 times 2k plus 1 over 2k plus 2 is less than 1 over root 3k plus 4. So let me call this inequality, let's say 2 star now. Now 2 star is equivalent with what inequality? Now 2 star is equivalent with saying that 2k plus 1 over 2k plus 2 is less than root 3k plus 1 over 3k plus 4. Right? Do you agree with this? See, this inequality is equivalent with this inequality. Why? Well, because to go from this inequality to this inequality, it's just enough to multiply both sides by root 3k plus 1, which is of course a positive number. And if you want to go from bottom to top, again, similarly, you just need to divide both sides by root 3k plus 1, and then you can go from bottom to top. Now, this inequality is equivalent with what? This one is equivalent with saying that 2k plus 1 over 2k plus 2 to power 2 is less than 3k plus 1 over 3k plus 4, right? Because, you know, a less than b, if a and b are positive, then we can say that a less than b is equivalent with a squared less than b squared, right? So here a less than b, we are saying is equivalent with saying that a squared is less than b squared, because a and b are both positive. Now this one is equivalent with saying that 2k plus 1 the whole squared is less than 3k 2k plus 1 the whole squared times 3k plus 4 is less than 3k plus 1 times 2k plus 2 the whole squared. Now, how did I get this one? Well, if you want to go from top to bottom again, just compare them from top to bottom. You just need to multiply both sides by basically the common denominator between these two fractions, which is 2k plus 2 the whole squared times 3k plus 4. If I multiply both sides by 2k plus 2 the whole squared times 3k plus 4, then left-hand side becomes this, and right-hand side becomes this. And of course, similarly, if you want to go from bottom to top, you have to divide by the same expression. And then this one is same equivalent with saying that, let's just do some algebra. 2k plus 1, the whole squared is 4k squared plus 4k plus 1 times 3k plus 4 less than 3k plus 1 times 4k squared plus 8k plus 4. And this is equivalent to saying that now if I expand 12k cubed plus 12k squared plus 3k plus 16k squared, 16k and 4. And the other side becomes, don't have enough space, so let's write here, and 12k cubed plus 24k squared plus 12k, 4k squared, 8k, 4. This is equivalent to saying that 12k cubed and 28k squared, 19k, 4, 12k cubed, 28k squared, 20k plus 4. Now, this one I can cancel with this one. Then 28k squared cancel with this one. Then 4 cancels with 4. I'm left with 19k less than 20k. And if I take this one to the other side, this is the same as k bigger than 0. If I take 19k to the right side, 20k minus 19k is k bigger than 0, which is true because k was, what do I know about k? Well, we wanted to show that the inequality holds for n bigger than or equal to 2, so k is at least 2. K is at least 2, and therefore, of course, is positive. So this one I can say which holds since k is bigger than or equal to 2. Okay, so this last inequality holds because by assumption k is bigger than or equal to 2, therefore positive. And then I can say, okay, because this holds, then this holds. And if this holds, the one above it holds, and then the one above, the one above, the one above. I go all the way until I reach 2 star, which is exactly what I needed to show. And I already established that it's enough to show 2 star, and 2 star holds because k is bigger than 0. So therefore, 2 star holds. And we already established, like I said, we already established that it's enough to show 2 star. And we just established that 2 star holds. Because why was it enough to show 2 star? Because if 2 star holds, then this guy will be less than this guy. And then that means left-hand side is less than right-hand side, which is what we needed to show in order to complete the inductive step. So we can say, hence, by induction, 1/2 times 3/4 times 2n minus 1/2n is less than 1/√3n plus 1 for n bigger than or equal to 2. So you can see that sometimes, when you are trying induction and to complete the inductive step, sometimes the computations would become a little bit long or messy, but just be patient and try to do all the algebraic computations that are needed, common denominators or simplifying inequalities to equivalent versions. And then at the end, if you get some inequality that it holds, either by assumption, which was the case here, k bigger than 0 was our assumption, or sometimes you get, for example, something that trivially holds. For example, sometimes when you calculate the equivalent versions of the inequalities that you want to show, at the end you get, for example, 2 bigger than 0, and 2 bigger than 0 of course holds, and then that means the previous equivalent versions hold as well. So just be patient when you do induction. Sometimes the solution could be long, like this example. So let's do another one, this time from a set theory. So example, this one is question 42. Suppose that A1 to AN and B are sets. Show that A1 minus B intersection A2 minus B intersection all the way to AN minus B is equal to A1 intersection to AN minus B for n bigger than or equal to 2. Okay, so let's first verify it for two sets. So basis steps of proof by induction. Basis step for n equals 2. If let's say A1 and A2 are two sets, then let's calculate the left-hand side and compare it with right-hand side. Left-hand side is going to be A1 minus B intersection with A2 minus B. So what is this? This one, if you remember, A minus B, if A and B are two sets, A minus B, same as A intersection B complement, right? So I can write this one as A1 intersection B complement. A1 intersection B complement intersection A2 intersection B complement. A2 minus B is into A2 intersection B complement. Then we can use the commutative property of intersection and write this one as A1 intersection A2 intersection B complement intersection B complement. All the operations, please note, that are intersection, and therefore we can write it in this form. Now B complement intersection B complement is of course same as B complement. So we can write it as A1 intersection A2 intersection B complement. Now any set intersection B complement is the same set minus B, right? That's the meaning of a set minus B. So we wrote this, we can write this as A1 intersection A2 minus B. Now what about so this is the proof for basis step, which means that we've checked that this inequality holds for two sets, for two arbitrary sets, A1 and A2. So please remember that the induction is on the number of sets. So in the basis step, I assume that there are only two sets. But which two sets? Those two sets are arbitrary sets. Could be any, could be, like I said, could be finite sets or infinite sets. But I just know that there are two sets, A1 and A2, and I verified that inequality, verified this equality or identity for two sets. And then in inductive step, we have to assume that the same equality here holds for k sets, k arbitrary sets, and then show that it holds for k plus 1 arbitrary sets. So again, the hypothesis, induction hypothesis, is on the number of sets. How many sets do I have? Well, in induction hypothesis, I assume that I have k sets. Any k sets that I consider, like A1 to AK, then the equality holds. This equality here holds for them, meaning that A1 minus B intersection A2 minus B intersection to all the way AK minus B is same as A1 intersection to AK minus B. And then I want to show that the same equality holds for any k plus 1 sets. So I have a new batch of sets, let's say k plus 1 sets this time, C1 to CK plus 1. So why am I using in new letters? Because in the induction hypothesis, I assume that the equality star holds for any k sets A1 to AK. Now these k plus 1 sets could be unrelated to the one that we consider in the induction hypothesis, A1 to AK. So these are any set of any collection of k plus 1 sets. And because the letter AIs have been already used, so I'm using a new letter, let's say C1 to CK plus 1. Okay, And then I have to show that the equality star holds for these k plus 1 sets. So I started with the left-hand side of the equality star, which means C1 minus B intersection C2 minus B all the way to CK plus 1 minus B. Now, if you look at the first part of this intersection, C1 minus B intersection to CK minus B, this first part, I can apply induction hypothesis for it because there are k sets here, C1 to CK. And I'm assuming that for any k sets, as long as the number of sets is k, then I can assume that the equality star holds C1 minus B intersection to CK minus B is same as C1 intersection to CK minus B. So this is the equality star, which is what we want to show for any cos k, which is what we are already assuming as a part of induction step, as a part of induction hypothesis. So induction hypothesis assume that this equality holds for any k sets. So C1 minus B to CK minus B can be written as C1 intersection to CK minus B. Now, okay, so this part, the first part is C1 intersection to CK minus B, then intersection with CK plus 1 minus B. And how can I simplify this further? See, I have something of the form, let's say D minus B intersection, let's say E minus B. D minus B intersection E minus B has already been simplified as a part of basis step. Look at the basis step. What did we do in basis step? We showed that if I have any two arbitrary sets, I call it A1 and A2 here. You can call it D and E, for example, if you want. Let's say D minus B intersection E minus B can be written as D intersection E minus B. D minus B intersection E minus B is always D intersection E minus B. So this is what we showed in basis step. So here also I have D minus B intersection E minus B. I can write it as D intersection E minus B. So by what we showed in basis step, we can also use the notation D and E here. D minus B intersection E minus B, same as D intersection E minus B. And now this part is basically my D intersection E minus B. And that's it. So this is the right-hand side of the equality star for k plus 1 sets. C1 intersection to CK plus 1 minus B. So we started with C1 minus B all the way to intersection CK plus 1 minus B. We showed that same as C1 intersection to CK plus 1 minus B. And therefore we proved star for k plus 1 sets C1 to CK plus 1, which completes the inductive step. So you can see that when you want to apply induction method, depending on the field, is it a set theory, is it number theory, is it in algebra or proving inequalities, then we have to use a little bit different technique in order to complete the inductive step. So I think the only thing I can recommend here is that you need to do lots of practice to get comfortable with the tricks that you have to do, or with the techniques that you need to do in completing inductive step. So please do lots of practice. I'll upload some exercises in the assignment. Please make sure you complete all those to get comfortable with how you have to apply the induction method in order to prove different statements. And of course, over years, when you complete other mathematical courses, you will do induction method as a part of proof for many types of questions in each field. Okay.